Okay.
So we are now in screening mode. Welcome everyone to this first session, first day of our ESPP webinar. We'll take just a few minutes for people to connect. We're ticking up towards 180 people joining. So we had 400, close to 500 people registering. So we'll see how many connects today.
Mm-hmm. Yeah, I think we wait a couple, 2-3 minutes more to allow everybody to join.
Perfect.
Message. Hello, Mohammed.
Yeah.
Okay, we still have people joining. I think now it's stabilizing around 210 people joining in. Okay, I think we can start. People are still a few people are still joining, but I think most are connected. So yeah, good thing about webinars, people are very much on time. So welcome everyone to the first day and the first session of the ESPP webinar on iron phosphate. I will let the ESPP president, Ludwig Hermann, to say a few words to kick off this meeting. Ludwig, please.
Good afternoon and good morning and good evening if you are joining from other parts of the world. Welcome on behalf of ESPP, the European Sustainable Phosphorus Platform, to our first iron phosphate workshop. So imagine we are now in Utrecht, as it was planned to be physically. Now we are sitting in different parts, and still I want to thank Ghent University for supporting us, for co-organizing, as well as INCOPA, INRAE in Rennes, and the projects PTRAP, SUSFERT, and of course, last but not least, WETSUS, represented by Leon Corwing. So all of you are invited to speak a few words or to introduce yourself after my introductory comments. Yeah, iron phosphate. So we all know that iron is very relevant for removing phosphorus from wastewater. We are not expecting any facilitating higher effluent values. On the contrary, the Commission confirmed that the wastewater directive will stay, and we rather expect in different countries lower effluent values as before and as currently. So we need, probably also in the future, we need iron to remove phosphorus from wastewater. It's the most efficient precipitant that we have currently available, but it traps phosphate as iron phosphate, and iron phosphate has issues, as you all know probably. We have problems to release phosphorus from iron phosphate in soils, and the efficiency of iron phosphate as a fertilizer is heavily controversial. So we are in a dilemma, so to say. We have on one hand we have a very efficient precipitant, and on the other hand we have a compound that is not the preferred one. Let's put it like this, at least if it comes to use as a fertilizer. So these issues, the pros and cons, as well as the different research projects that we have seen, most of them more recently, that pursue finding solutions for the dilemma, are discussed during this webinar. And I thank you very much for joining. I thank our panelists for participating. I thank our co-organizers for having supported us heavily, and I think the number of attendance is a big success. So may I just ask our co-organizers to say a few words. Sarah will introduce them. Thank you very much.
Thank you very much, Ludwig. Thilo, would you like to start to say a couple of words?
Yes, thank you, Sarah. So good afternoon, everybody. My name is Thilo Behrends. I'm Associate Professor at Utrecht University. I'm also coordinator of the PTREP project. So I will introduce the PTREP project in the first presentation of the workshop. And when Sarah and the ESPP approached us at the beginning of the year with the idea to co-organize this workshop, I was extremely excited because I thought this would give an excellent platform and possibility for our PhD students and for the whole consortium in the PTREP project to connect to other scientists and shareholders in the large field of being interested in the sustainable phosphorus use. And yeah, I would have been very happy if it would have been possible to welcome you everybody in Utrecht for a physical meeting. But we already discussed before this meeting that on the other hand, with this remote version, we possibly have the opportunity to reach a much larger group that we possibly could have welcomed here in Utrecht. So I think this is also very beneficial. And I hope that everybody will enjoy this workshop, but I also that this will stimulate more exchange within the group who is interested in iron and phosphorus and its connection. Thank you, Sarah.
Thank you, Thilo. We also have another co-organizer here, Caroline Anderson from CEFIC, representing INCOPA. Would you like to say something, Caroline?
Yes, good afternoon, everybody. So my name is Caroline Anderson. So like Sarah was mentioning, I'm the manager of INCOPA, which is the European Inorganic Producers Association, part of CEFIC, based in Brussels. We have 29 member companies across the EU then producing both aluminium and iron salts. And of course, with various usages for water treatment, paper manufacture, etc. The INCOPA membership represent more than 85% of the total European coagulant production, and therefore we are of course very interested in this webinar, and we are very happy to be co-organizer of this event. And you will hear more from Jean-Christophe Adès from Kemira about our specific INCOPA activities related to phosphorus removal and recovery and contribution to a circular economy. So thank you very much.
Thank you, Caroline. We also have here Marie-Line Daumer from INRAE Rennes. Please, Marie-Line, a few words.
Yes, good morning, everybody, and thank you for inviting me. So I'm Marie-Line Daumer. I'm working at INRAE, which is the French Public Research Institute merging of INRAE and IRSTEA. And I've been working on peer recovery for nearly 20 years now. First from to recover phosphorus before sludge spreading or incineration, even in wastewater treatment plant using iron or aluminum salts for peer removal. And so it's a pleasure to be here today.
Thank you, Marilene. Finally, we have Leon Corving from WETSUS here. There, yes. Please, Leon. You're on mute.
Sorry. Thank you for the introduction. I'm Leon Corving of WETSUS. WETSUS is a Dutch research institute focusing on water technology. We try to be a bridge between academia, the universities, and industries, and we work together with more than 100 companies on new developments in water technology. And a couple of 6-7 years ago, we started working on iron and phosphorus interactions because we thought there was a gap to recover phosphorus from these compounds. So it was really nice now to see also this workshop and this increased interest in iron phosphate interactions, and we gladly supported this workshop. And good work, ESPP, for organizing this.
Thank you, Leon. So after this round of introductions of the co-organizers, I think we'll just head on to the actual session because we have a lot of speakers today. So before we start, I just would like to mention some housekeeping rules for this webinar. So as I mentioned, we have a lot of speakers, so we will just have room for 1 or maximum 2 questions after each speaker, and hopefully we have time in the end of the session for more questions. So you can put your questions in the Q&A box, and my colleague Chris Thornton will help me to pick up questions for the speakers. Since this is an online event and will not have the possibility to chat over coffee in the breaks, I do encourage you to use the chat function to discuss, and you can also respond to questions there if you have some input for that. Yes, for the rest, I think we can move on. So our first speaker is Thilo Behrends from University of Utrecht. Please, Thilo, the floor is yours. The screen is yours.
So yeah, thank you very much, Sarah, for this introduction. And as I mentioned previously, I would like to introduce to you the PTRAP project. And I was also asked to give an introduction in the challenges of trapping and recycling phosphorus from agricultural runoff. And I decided, as this is the first presentation within the project, in this workshop, not to focus so much on the challenges of trapping and recycling, because these issues will be presented later by PhD students and principal investigators in the project who also give presentations in this workshop. But I will more focus on the context of the PTRAP project and explain why we target phosphorus in agricultural runoff. So the PTRAP project is an innovative training network, and there are 11 PhD students working in this project at several research institutions in Europe, but also in private companies. Additionally, we have 7 partner organizations which are shareholders in the research. For example, this includes fertilizer companies or water authorities, or other companies who are interested in the research being performed within PTRAP. So the project has launched in March 2019, but most of the PhD students started at the end of 2019 and at the beginning of 2020, which was a little bit unfortunate in view of the Corona shutdowns. So the overarching goal of PTRAP is to contribute to improving the quality status of surface waters by reducing the phosphate loading. And we do this by tackling 2 different pathways for phosphorus input into surface water. So we are particularly addressing the phosphate flux out of agricultural areas, and our goal is to capture and recover this phosphate from the agricultural runoff. On the other hand, there's also the approach to reduce the internal phosphate loading in lakes. However, I'm not going to talk a lot about the second approach in this introductory presentation. However, this will come back later in this workshop. To explain why we tackle this, this leaching of phosphorus from agricultural soils, I want to take you to the phosphate streams in agriculture in the 1970s, when we have intensive agriculture. Then the phosphate was added to soils in the form of fertilizers, which were predominantly produced out of phosphate ores. And once this phosphate has entered the soil, it could have been taken up by the plants, and then it could leave the system and being harvested. And when there has been not efficient removal of phosphorus in sewage, eventually, due to the consumption of agricultural product, it has ended in surface waters through the sewage. The other possibility is that the phosphate in soils can be leached out in surface waters directly. However, there's also the possibility that this phosphorus is moving to compartments which are, in which the phosphorus has residence times of longer than 100 years, which I called here stabilization of the phosphorus in the system. So this idea of using phosphorus fertilizers, which are produced by ore mining and discharging the phosphorus eventually in surface water, has two major problems. And one problem is the supply of phosphorus from due to the mining of phosphate ores. And one aspect, or phosphate mining has several issues. One of this is a geopolitical issue. That is that the phosphorus reserves of economical interest in phosphate is controlled by only very few countries in the world. And if you look on Western Europe, there's practically no economically interesting reserves in phosphate ores. Secondly, phosphate mining has the problem that it also releases heavy metals or uranium, which comes with phosphate mines. And third, obviously this is a limited resource, and with the increasing demand for phosphorus in the world, we might run out of phosphate ores eventually. The other aspect is that this excess of phosphate into surface water causes ecological problem, as most of you might be aware of. So this is an overview about the quality status in European waters based off an European Environmental Agency report from 2018. And this shows criteria to assess water quality, and one of these criteria is the phosphorus conditions. According to this overview of all lakes, but it's practically the same for all rivers in the European Union, it seems that only a relatively small fraction, which is maybe like something like 15%, has then a status less than good. However, if you also take in consideration that about 40%, for 40% of the lakes and rivers, this information is not available, the fraction is significantly larger. And in particular, when it comes to lakes and rivers, which are directly connected to areas where we have intensive agriculture. So how could you now tackle this problem? And one obvious approach would be to reduce the export of phosphate from sewage into surface water. And there's been made huge progress by improving the removal of phosphorus in wastewater treatment plants. This reduces the phosphorus fluxes into surface waters, but it does not solve the problem that we still rely on phosphate for mining activities. So the ideal situation then would be that this phosphate, which is retained in wastewater treatment plant, returns into the agricultural cycle in the form and is converted into a fertilizer to reduce the dependency of phosphate ores. And we will hear several presentations throughout the workshop on efforts to close these agricultural phosphate cycle. However, there's still this possible export of phosphate from soil into surface water. And the question is, how relevant is this leaching of phosphate? To convince you that this export of phosphate from soil is still a major issue, I want to give you one example, which is based on data from a study by McCracken in 2018, and they did a phosphorus budget in the whole Baltic Sea catchment. And what I want to show is that the main problem we have in this today is actually not the excess of phosphorus, which is the surplus of phosphorus actually added to agricultural systems, at least in Northern Europe, but it's the legacy phosphorus. So what is being presented here is actually the annual flux of phosphorus in kilotons per year into the whole Baltic Sea catchment as since 1900. And this is the black line. And what it shows is that there has been a net anthropogenic P influx, which comes from import, which includes import and export of agricultural goods. But the main component here is the fertilizer import, which is this blue area. So the red area shows the phosphate, which has so far been exported as a waterborne P flux into the Baltic Sea. And this reflects only 6% of the total phosphorus which has been accumulated in the whole Baltic Sea catchment, which means 94% of this phosphorus is still in this catchment. This is the legacy phosphate. So according to this conceptual simplified model by McCracken, we can ask ourselves, where is this phosphate now? And they distributed over two pools. One is called the mobile pool and one is the stable pool. And what is shown here that a considerable part of this excess phosphate has ended up in the mobile pool and has built and reached a maximum in the middle end of the 1980s, and it started to decrease by then, whereas the predominant sink has been actually the conversion into the stable pool, which is, for example, the burial of phosphate-containing sediments into the deeper part of lakes, for example. So the consequences that a considerable part of the legacy phosphorus ended up in this mobile pool is actually leading to the situation, if you look at today's export of waterborne phosphorus into the Baltic Sea, that the main source is this mobile legacy. So then the question arises, how does this mobile legacy reach the surface waters or reaches the Baltic Sea? For this, I want to present you results from a study by Bauer et al., which was published in 2019, of one specific catchment draining into the Baltic Sea. This is the Warnow Basin. And they looked in detail into the different source terms for dissolved reactive phosphate in small rivers within this catchment. And they distinguish different pathways for the transport from the catchment area into the surface water. And one pathway is wastewater treatment plants, and these are the black bars, and you see that currently the import or the flux from wastewater treatment plants is only a minor contributor. And then there's a contribution of dissolved phosphorus in deep aquifers, in shallow aquifers, and in drainage water. And I emphasized here the drainage water, which is shown here at the most right bar. So I don't want to elaborate about all other parts. But what it shows is that in several areas, which are representative for highly intensively used agricultural areas with relatively flat topography, which also have drainage systems, almost half of the total phosphor export goes through the drainage system. And this is an opportunity because the outlet of tile drains and drainage ditches are points at which we can intercept these phosphorus fluxes. And this is actually what we aim for in PTRAP. So we want to intercept the export from phosphorus from agricultural soil in drained areas. And we not only want to intercept it, but we also directly want to go one step further. It means we also want to find possibilities to use the captured phosphorus as a valuable product for agricultural applications, preferentially a fertilizer.
Thilo, we're running a bit. Okay, you're wrapping up. Thank you.
Just 2 more minutes. So 1 minute, I can quickly go through it. So all other approaches and techniques within PTRAP are based on this close affinity of phosphorus for iron. So in terms of how we want to trap or intercept the phosphorus flux, we will rely on systems which have been developed in our within partner organizations and beneficiaries of the project, which rely on iron-containing byproducts from drinking water treatment, and to build filter systems within drainage systems. So one of the possible strategies to recover the phosphorus which is bound to iron oxides, which is an iron 3, is to reduce it and form Vivianite. It has been mentioned at the beginning that Vivianite might not be the preferential product. However, within PTRAP, we're also looking into possibilities to use this Vivianite, for example, as a suitable iron and phosphorus source in soils. And this will also be presented later in 2 of the presentations within the workshop. So if you want to learn more about this, I would like to refer to our webpage, and these are the references. Thank you very much.
Thank you very much, Thilo. Chris, did you pick up some good questions that we can direct to Thilo from the chat?
Yes, I have a question from Mohamed Salutar Islam Mazumda. In slide 10, the cause behind the decrease of phosphate after 1980 was not clear. Can you explain, do you have an explanation of that? Slide 10.
Yeah, there have been 2 decrees. I cannot directly recall to which one you refer, but obviously there was several European directives implemented to reduce actually the phosphorus surplus in agricultural applications, and this drastically reduced the import of fertilizers to agricultural soils. The fact why the mobile pool is decreasing according to the model calculation, this is mostly due to the transfer into the immobile pool in this moment, but on a long term, this is supposed to decrease further. Then when you reduce the phosphorus import in the system, actually this will be the long-term source fueling the phosphorus export from agricultural soils.
Thank you. We are now moving on to 4 flash presentations on exactly this first step on trapping phosphorus from agricultural lands. So we first have a presentation from Stefan Jansen from Deltares. Please, Stefan.
Yes, thank you. I will share my screen. Let's see if it works. Yes, can you see my screen?
Yes, you can make it into, we see all your screen. Maybe you can make it to a full screen mode.
And is it now full screen for you?
Yes, now I think it's good.
Yeah,
okay.
Thank you very much. Well, Thilo, thanks a lot for the introduction, because you draw the overall picture very well. What I will present here is some examples of field experiments we did on the use of iron sand to trap P from agricultural drainage. And here you see a nice picture of one of these locations with nice Dutch flower bulbs. Actually in the Dutch flower bulb area, phosphorus is a big water quality problem. And like Thilo already mentioned, this is exactly an example of a legacy case. So the groundwater here has a high concentration of phosphorus after years of mainly organic matter use. So even if we would start or change agricultural practice here now, the legacy of phosphorus coming into surface water would still go on for decades. And here also this very good example of a drainage system where the phosphorus is entering the water system easily via the drains. So it's an excellent case to apply filter systems. And that's exactly what we try to do in this project. And we used iron-coated sand for this. Well, iron-coated sand is a side product of drinking water production from groundwater. To remove the iron from the groundwater, it is led through filters, through sand filters. And well, over time, these sand filters become saturated with iron oxide. And in this way, you have an excellent filter material as a side product from the drinking water production. And well, these iron sand grains are an excellent filter material because of a couple of factors. Well, of course, it's low-cost material as it's a side product. It has this very strong phosphate binding, good permeability. There's actually various grain sizes, which makes it a very suitable filter material. And there's no side effects, except for, well, we have to check the material for arsenic, which could be present because of its presence in groundwater. But once checked for that, there's no side effects. Well, this is a couple of pictures of the field pilots that we did with this material. And as you can see, we tested various technological forms for the filter material to be applied. So in the right top, you can see a drain, tile drainage, which is enveloped with iron-coated sand. It has the advantage that you very directly trap the phosphorus before it's coming into the phosphorus cycle, and you don't need any added area of the land, which is very very valuable land. The disadvantage, of course, that you have to install drainage pipes. But well, if a farmer wants to install drainage, which is done for about 50% of the Dutch agriculture area, it could be a very good application. Well, if you go down one picture, you see the other application that we tested. This is a filter structure when the drains enter the ditch. It has the advantage that you can have more control of the filter material, and you can also replace the filter material when needed. The disadvantage, of course, that you need some area here, but here we found enough area in the ditch. And well, the last application is the bottom left picture, where a reactor system was built. Well, this in terms of phosphorus removal, this worked well as well. But here we saw that there's more risk of clogging because ditch water was fed into the reactor. And you can see that a pre-filter was needed for this, but even then, clogging issues arise. So clogging can be an issue if you do use that, that technical form. Well, overall, the results were that phosphorus removal rates can be very high, up to 80 to 90%. The form of phosphorus that's being trapped is orthophosphate. So if you have a lot of organic phosphate, this will not be trapped. Between the different varieties, the cost of maintenance and the maximum lifetime varies. But if you look at lifetime, we could constrict these kind of forms for about 10 years of application. And some challenges still are present. Well, surprisingly, not so much the removal efficiency, but they are more in the field of practical applicability, how to make these kind of structures so that they remove phosphorus, but they are also applicable in normal agricultural practice. A very important issue is the stability of iron oxide coatings at low redox potentials and high flow rates. Recently, we saw issues with these. For instance, that at low redox potentials, the iron oxide might dissolve or loosen from the sand grains, and it might lead to phosphorus remobilization. And well, permeability was already mentioned, and of course, costs and more practical experience are very important issues for further practical application.
Stefan, could you please wrap up? We're running a little bit late. Thank you.
Yeah, this is the last slide. So, well, to actually look into this practical application, it's interesting to note that there are two field scale trials going on at this moment, at a full agricultural field scale, where this type of system has been constructed 2 years ago. And we are currently monitoring these systems to find out how well the iron-coated sand is behaving here to trap phosphorus. So that was the presentation. Thanks very much.
Thank you very much, Stefan. We're running a little bit late, so I think we'll have to just continue straight to the next flash presentation. That will be by Hui Xu from Ghent University, and I will share the screen.
Thanks, Sarah. My name is Hui Xu from Ghent University. Good afternoon, everyone. Thanks for having me here. And I would like to thank Thilo and Stefan to fulfill the background, good introduction. So my slides will be very short. In Flanders, north part of Belgium, agricultural diffuse phosphorus loss is a major cause of eutrophication problems in surface water because of intensive fertilization from last century. 17% of agriculture field is drained in Flanders. Within the drainage system, we have
Sorry, I was sharing the wrong screen.
It's all right. I will just continue. So within this drainage system, we have one concentrated source of nutrient supply to the stream where could be tackled P filter. We developed a filter to remove P, and the figure on
Sorry.
So you see the figure on the left. It shows how the filter works. It is installed at the end of the drain. Water enters the filter from the drain in the left side. It goes at the bottom to the right, then upwards. Water has reaction with the filter material, iron-coated sand, and eventually goes out to the beach. Two important features here: mesh netting at bottom and top to stop big particles, and upwards oriented outlet to let the sediment, possibly particular P, stay at the bottom. So there are a few advantages of our filter. Low-tech solution, it is suitable for individual drains and very easy to install and operate. High performance. P removal efficiency is very high, up to 80 to 90% over several drainage seasons at different locations. It's cheap and safe. As Stefan already presented, the filter material is iron-coated sand, byproduct of drinking water industry, so they're rather cheap and don't cause any other contamination. Also, this filter has no impact on accessibility and landscape. Therefore, this filter could be potential solution to reduce P loads. Thank you. If you have any question.
Thank you, Hui. Sorry for my bad screen sharing. So we will do all four flash presentations to catch up a little bit. So next presenter is Hans Chr Bruun Hansen from the University of Copenhagen. Please, Hans.
Thank you very much, Sarah. Can you hear me?
Yes, thank you. So please,
okay.
2 minutes for you.
Yes. So I will present, we have been in a project similar to the one Thilo is now running. It was called Supreme Tech, a project to look at phosphorus filters in the landscape. And essentially there are two types of filter materials to trap P: alkaline materials, calcium-based usually, that are based on precipitation, and then there are metal oxides, iron or aluminium oxides. And we've been working with the last type of filter materials, and actually was a spin-off from this filter. So as Thilo also said, there's a lot of phosphorus stored in soils. It slowly is released. The concentration in agricultural drainage water is usually low, but we want to make it even lower to prevent eutrophication. Another challenge is that the water comes in huge volumes. So if you have a catchment of let's say 100 to 1,000 hectares, it's thousands of cubic meters of water every year. So these filters at end of the pipe have to be made of very permeable material. So we also had this goal to make such a filter. We didn't use the iron oxide coated water treatment residuals. Those that we can get in Denmark are usually too much arsenic. So we were thinking about another material. Could we also have internal storage in the filter granules? So we looked at porous granular supports, and here took a calcined diatomaceous earth. It can be provided in particles 2 to 4 millimeters, and also the porosity, the internal porosity is very high. Therefore, our strategy has been to impregnate and to precipitate the iron oxide in the internal space of these diatomaceous earth granules. So we You can see here to the right that we have the diatomite shells and it's full of pores, and then we precipitate the iron oxide in it, and the material looks like an iron oxide coated sand, you can see. So we get this material, we load it with 3 to 10% of iron. It has a specific surface area in the range here of 20 to 70 square meter per gram. It has a very high porosity, so for the whole filter, it's about 80%. Pore sizes are in two classes. There are very small pores, but also a fraction, a bit larger pores. The permeability, you can see here, the hydraulic conductivity is high. So we are now testing it in a field here for agricultural drainage water. The permeability is high, so it enables high flow. It has a relatively high P storage capacity. The idea here is that phosphate that is soaked on the external surfaces of the particles is moved into the internal and are stored internal within the granule, and then the sorption sites on the surface are continuously renewed. It's a physical stable material, but of course also I can dissolve under reducing conditions. We can recover P from the material. And then there's a usual precaution, as it was also mentioned previously. If there are particles, it will clog the filter. So you need a filter, you need a particle filter before this one to before you get the water into the reactive filter. This filter material, there's a startup company here, Dear Pure, in Sweden, that is now fabricating the filter material. Yes, that was my short presentation.
Thank you very much, Hans. That was very interesting. And we'll now hear from another speaker from University of Copenhagen, Changyong Lu. The screen is yours.
Yes, thank you. I'm gonna share my screen. Okay, good afternoon, everyone. I'm Changyong Lu from University of Copenhagen, who work with Professor Hans Chr. And today I would like to give you a short talk about the stability of magnetic LDH solvents for phosphate removal, which also a project of our group currently working on. As you probably know, the layer double hydroxide, or the LDH, is also reported properties in phosphate solvents, also for phosphate recovery, as it has high absorption capacity, fast absorption rate, and it can be regenerated by treat with the base or alkaline solutions such as sodium hydroxide. And it is reported to absorbing phosphate by ion exchange, surface complexation, or some are also observing the formation of the precipitation. But there is a problem, hasn't be or lack of knowledge is what is the stability of this material if you want to use it for a really long time and after many regeneration cycles. And another is what is the real P-sorption pathway during the various conditions at different pH or at different phosphate concentrations. To do that, we have synthesized magnetic magnesium ion LDH materials, which is also a very traditional LDH. And during the P-sorption, we found that after the TEM images on the top, showing that the residual solids after P-sorption at low phosphate concentration should indicate the LDH was dissolved and forming some amorphous rehydrate phase at such as at pH 5 or at pH 8, and it should remain intact at pH 11. And we further trying to distinguish distribution of the absorbed P at different phases. Image at the bottom left showing a P sorption isotherms This is the 3D surfaces at different pH and also at various equilibrium phosphate concentration. And the color bar is the amount of the phosphate, soft phosphate distributed on different phases. As you can see here, the material has a really high sorption capacity at low pH, which also reported by other researchers. We found that the phosphate actually was absorbed on ferrihydrate, not really on LDH, because LDH was already dissolved. And when at the pH neutral condition, when the phosphate concentration is lower, and the phosphate mainly absorbed on ferrihydrate or the remaining LDH, we also observing the magnesium phosphate precipitates formed at a really high concentration of the phosphate. And when we further increase in the pH up to like 10 or 11, most of the phosphate is absorbed on the remaining LDH. And if we go into really high phosphate concentration, phosphate is majorly solved by varying the formation of the magnesium phosphate precipitates, and the LDH was also dissolved. Right now we have a preliminary concentration. As we could see that the magnesium ion, LDH, could be dissolved under pH neutral or like weakly acid conditions. And the high concentration of the phosphate could also stimulate the dissolution of the LDH even at a high concentration. And we also found that the dissolution of the LDH could lead into some formation of amorphous ferrihydrate phase, which also has really high absorption capacity of the phosphate. And for the absorption mechanism, I think we found that the phosphate mainly stopped via the formation of the magnesium precipitates at alkaline pH at a high phosphate concentration. And so we think about that this material is actually was not really stable for long-term use, and we are supposing that if we want to use this for practical application, we have to focus on increasing the stability. And I'm only showing one result, which is magnesium ion LDH, but other well-reported LDH such as calcium ion or like magnesium aluminum LDH is also observing a similar phenomenon. So we are supposing that our finding has a general impact on a lot of LDH materials. And if we want to using LDH in wastewater treatment or phosphate removal, we are considering that we have to focus on how to increasing the stability. Okay, thank you so much.
Thank you so much, Changyu. We're running a little bit late, so I think we'll just have to move on to the next presentation, and I hope we can catch up with questions in the end of the webinar. Otherwise, we'll try and pick up questions and ask the presenters to respond to them afterwards and share with you. So next speaker is Lena Heinrich from Leibniz Institute of Freshwater Ecology and Inland Fisheries. Please, Lena.
Thank you very much. I am sharing my screen. Here it is, I think.
Yes, perfect. You're in slide share mode.
Perfect, thank you. So hello, everybody. Thank you for giving me the opportunity to talk here. Let me quickly introduce myself. I'm a doctoral student at the Leibniz Institute of Freshwater Ecology and Inland Fisheries. And I'm working on two different systems, the lake sediments and the wastewater treatment plants, but they have a similar behavior of the iron and the phosphorus coupling. Therefore, I'm relating to a subset of these systems. And this is iron-rich lakes and sewage treatment plants with application of iron dosing. And I will introduce the changes of iron and phosphorus coupling in these two systems with a decreasing redox potential, which in both cases is caused mainly by the degradation of biogenic material. The redox potential decreases in the lake sediments from the water column towards the sediment and then also within the sediment depth. And the dotted arrow indicates that the redox conditions can alternate in this system. In the wastewater treatment plants, the reactors are separated and direct potential decreases from the activated sludge system to the digestion. So this is a change with time in the process chain. And this is also the agenda of my talk. I will try to give an overview of the main processes playing a role. They are written in red here. This is the phosphorus release, the phosphorus immobilization towards anoxic conditions, and the competition with other binding partners for the iron. So what are the goals of such a study of two different systems with a similar iron and phosphorus coupling? The main goal is to optimize lake management measures to prevent the eutrophication by phosphorus immobilization under anoxic conditions, benefiting from the iron by controlling these key processes. And due to the similar dynamics, we want to use the sewage treatment plants as large-scale laboratories for the lake. So let's start with the first point of the agenda, and this is phosphorus release under anoxic conditions. And I'm referring here to the iron wheel. The iron wheel works as follows. In an anoxic water column, ferric iron has a low solubility, and it is precipitated as iron hydroxide, and this absorbs phosphorus well. And then the iron phosphorus particles reach the anoxic sediment, and after reduction, ferrous iron has a higher solubility and is therefore dissolved together with the adsorbed phosphorus, and both can diffuse towards the water column and towards the sediment deeper depth. However, if the water column is oxic, at some point iron is oxidized again, and then it can bind phosphorus again, and then the process starts all over. If the water column is not oxic, then phosphorus cannot be bound by the ferric iron again, and it can then enter the water column and then become available to all the growth. The second point of the agenda is the phosphorus immobilization regarding anoxic conditions by iron. And we see here data from an iron-rich lake. This is Lake Müggelsee, which is located in Berlin. And on the other side of the slide, we see data from an iron dosing sewage treatment plant, which is also located in Berlin. We sampled the depth layers of the lake sediment, and we sampled sludge from the different sewage treatment reactors, focusing in both cases on the redox decrease. And then we analyzed the fresh sediment and sludge by a sequential extraction, which is designed for phosphorus binding forms in freshwater sediments. And I will only explain the most important fractions. Therefore, I would like to direct your focus to the orange and the blue bars. The orange bars here and here indicate redox sensitively bound phosphorus. So the phosphorus that is maximum desorbed from dissolving iron hydroxides and also manganese compounds under anoxic conditions. And these conditions is mimicked by the reducing agent bicarbonate diphenite with a subsequent digestion of phosphorus compounds to orthophosphate, which is then analyzed. And the blue bars here and here indicate phosphorus that is released by a 1 molar sodium hydroxide. And this indicates phosphorus that is bound to, for example, redox stable iron oxides and Vivianite, that was not dissolved by the previous reducing step. So therefore, the design of the fractionation scheme is helpful to determine between the redox sensitive and the redox stable iron bound phosphorus in iron-rich systems. And we see the orange bars decrease and the blue bars increase with decreasing redox potential in both systems. And this indicates an immobilization of the iron-bound phosphorus regarding anoxic conditions. In addition to the sequential extraction, we studied these two systems by microscopy, XRD, and XRD quantifications. And these methods demonstrate that the redox stable iron binding, phosphorus binding form bound to iron is related to the ferrous iron phosphorus mineral Vivianite. So adding this process to this scheme, we see that iron oxidation and subsequent precipitation is not the only possible iron-phosphorus coupling in the lake sediments. However, it seems that an oxic water column is still beneficial for phosphorus binding also by two-valent iron, as the iron hydroxides with the adsorbed phosphorus deliver both binding partners to the sediment. And I would like to point to the importance of this process by an exemplary field study at Lake Großklinike in Berlin. After the iron amendment in 1992, the iron and phosphorus contents in the sediment increased and stayed much higher than the background before 1992. The iron-related phosphorus fractions accounted for 80% of the total phosphorus found in the sediment, and Vivianite was identified and it was abundant. And what we see in this sediment is the combined effect of the iron wheel and the phosphorus immobilization by iron. So the iron wheel is active and it is recycling iron to the surface of the sediment. But also the immobilization by two-valent iron is active and it can stabilize phosphorus against the dissolution under anoxic conditions. However, iron amendments do not always work that well. After the iron amendment at Lake Plötzensee, also in Berlin, the iron content increased, but after a few years, the content was almost back to the background value. And after the removal of the phosphorus in the water column at the moment of the iron amendment, there was no indication that the iron in the sediment of this lake was or is a phosphorus sink. The iron-related phosphorus fractions account for less than 40% of the total phosphorus found in the sediment over the whole profile, and Vivianite or other stable iron-phosphorus minerals have not been identified. Sorry for that. But instead of the phosphorus in this sediment, sulfur clearly coincided with iron in this in the profile. The units of the iron and the sulfur are not contents, but they are accounts from micro-XRF scanning. And we also identified pyrite over this whole profile, but approximately twice as much within this iron peak. This was done by. So this competition with other binding partners is the last of the three principal processes that play a role for the coupling of iron and phosphorus in lake sediments. Sulfur here is not the only possible competitor for phosphorus with the two-valent iron, but it is the most prominent in the lake sediments. And the sulfur bound to the iron as sulfide can originate from organics or from sulfate reduction. So I would like to quickly go back to the goals I set at the beginning of my talk. How can this knowledge help us to optimize lake management measures, preventing eutrophication by preventing the phosphorus dissolution and promoting the sediments as a phosphorus sink? So firstly, anoxic water column prevents the dissolution of phosphorus to the water column and delivers also the binding partners, iron and phosphorus, to the sediment. And then the red stable ferrous iron phosphorus mineral can form and immobilize phosphorus in anoxic sediments. But the competitors like sulfur need to be included in the planning of management measures using iron. So there it would be interesting to minimize sulfate reduction, for example, by reducing sulfate loads. With this, I thank you for the attention. I don't know if it's time for questions. Thank you.
Thank you, Lena. Excellent timekeeping. Chris, can we squeeze in one question? Do you have something from the audience?
Yes. How does the natural organic matter impact the iron phosphate reaction?
So in multiple ways, I would say. So firstly, as I said, the redox decrease is mainly caused by the decomposition of the organic matter. Then also organic matter can interact with the iron by complexation. Yeah, maybe there are more ways.
Okay, thank you. Let's move on to Caroline, who will speak more in detail about interactions in natural sediments. So Caroline Slomp is a researcher at Utrecht University. Please, Caroline.
Okay, I'm trying to see my presentation, but I see it's not popping up, so I'm going to try something quickly. Oh. I'll try again. This is the first time I have a brand new computer. This is the first time I'm trying Zoom. But
normally you have a green button somewhere saying share screen in the Zoom window.
Yes, I'm pressing on the share screen, but my my PowerPoint's not showing up. So that's the thing, my PowerPoint window. Do you see what I mean? Well, maybe you can just show my slides.
Okay, yeah, I will do that.
That's best. I'll just say, this is strange. It's unfortunate. I have a new computer, as said, so.
1 second. I hope
Maybe while we wait a question to Lena, what is the minimum concentration of sulfate or sulfur that will inhibit the iron phosphate reaction?
For the sulfur or sulfate? For the sulfur, there is a ratio which is between 1 and 1.5 sulfur iron ratio in the sediment, in the solids. That has been shown in a previous publication to be inhibitory. However, it is, I would say it's hard to say how much sulfate load can come to the water column, because that also depends on the sulfate reduction rate.
Okay, I'm sharing my screen. I hope it's better this time.
Screen? Okay, thank you very much. Okay, I will start. So, well, thank you very much for this invitation to talk here. I will like to tell you something about the role of iron phosphorus phases in burial of phosphorus in coastal marine sediments. And this connects very nicely to the previous talk by Lena. So next slide, please. So if you look at the classical view of sinks for phosphorus in marine sediments, people think that's organic phosphorus, iron oxide bound phosphorus, and also oxygenic minerals that are formed. And this can be in marine sediments. Usually it's thought that that's apatite, so carbonate fluorapatite. And if you show me the next slide, the case I want to make here today is that we should also consider minerals that are typically thought to only occur in lake sediments. And one of those minerals, one of the most important ones, is Vivianite, so an iron 2 phosphate. So next slide, please. Yeah, so when does Vivianite form? That was just explained by Lena, and we know that it forms when you have a lot of dissolved iron, when you have sufficient dissolved phosphate, and if there's not too much sulfide around, because that sulfide will like to, will like to react with the iron 2 and precipitate as iron sulfide, and also form pyrite. So essentially what you need is no sulfide, high iron, high phosphate. And what we see is that in marine systems, we find that at low salinity. And what we also see is that it can also occur at a higher salinity, but then below the zone where methane and sulfate react with each other. So below the zone of anaerobic oxidation of methane and sulfate. Now, if we now look at what evidence we have for Vivianite in marine sediments, and actually if you look at lake sediments too, it's actually quite difficult to prove that Vivianite's there. And people often use pore water profiles, saturation state calculations from that. They use sediment phosphorus enrichments, and they often use the observations of blue crystals, because Vivianite turns blue when you expose it to oxygen. And those blue crystals are then used as indications of Vivianite. Next slide, please. And so why is Vivianite so difficult to really quantify and really prove that it's there? Well, essentially, as was just shown, we like to use sequential extraction procedures to determine Vivianite concentrations. And if we look at the one that's most used for marine sediments, the so-called SADEX procedure developed by Kathleen Ruttenberg in 1992, we see that the second step targets iron-bound phosphorus. And that step targets both iron oxide-bound phosphorus and Vivianite. So they're combined in one step. And so usually when people extract this iron-bound phosphorus, they say, oh, it's all iron oxide-bound phosphorus. But the case I want to make here is that in some cases, it might be almost completely Vivianite. Next slide, please. So the goal of our studies over the past years on this topic has been to detect and quantify Vivianite in these coastal sediments. And we have used a combination of techniques. We've used micro XRF, we've used these SADEX extractions that I just mentioned. We've used synchrotron-based stains, we've used electron microscopy, and also X-ray diffraction. And we've combined this with a lot of information about the sites that we've studied to understand the conditions of formation. So we have a wealth of additional geochemical and microbiological data for a lot of these sites. Next slide, please. But today I'm going to show you only something for the Botnian Sea, a location that is a very nice illustration of these processes that I'm mentioning. And this is a location in the northern Botnian Sea, so in Swedish waters. And these sediments are very iron and phosphorus rich. Next slide, please. And what we see in these sediments is, and at the top you see sulfate and methane, these react with each other. Below that, in a zone where there's no longer reduced sulfide, so no longer H2S, what we see there is extremely high iron. And I'm not sure you can all see it, but the concentrations there go up to almost 2 millimolar, which is really high. And we also see that phosphate concentrations directly drop off below that shaded area, below that sulfate methane transition zone. And we've indicated this, or we've interpreted this as the zone that in this location below the SMT set, that is where likely Vivianite is forming. So we thought this is a great place to assess if this is the case. Next slide, please. And so what we did first was see, okay, if we use that SADEX extraction, do we find iron-bound phosphorus? Well, we did, and we saw a lot of it. And you can see that here, those high concentrations below that shaded area, that's where we see iron-bound phosphorus. But what fraction now is Vivianite? Next slide. Well, to look at that, we embedded the sediment in a resin and then looked at it with X-ray fluorescence. And you can see all these little dots, all these little stars that show up at depth in the sediment. And if you zoom in further, you see that these are in fact crystals, and these are crystals rich in iron and in phosphorus. Next slide, please. And if you then use synchrotron-based stains, you can show that this is in fact Vivianite. So all of these dots that are showing up, all of these enrichments at depth, they're all Vivianite. Next slide, please. And another technique you can use is you can sieve the sediment, and if you have these large crystals, you can then separate the sediment from, you can separate the Vivianite from the rest of the sediment, and you can look at it with optical light microscopy. You see here a blue crystal. So you can see we tried to not expose it to oxygen, but there was apparently a little bit of oxygen exposure leading to this blue color. And then we have on the right-hand side scanning electron microscopy images of a Vivianite crystal. Next slide, please. What you then can do is you can take a lot of these crystals that you've sieved, you can take that fraction and do XRD with it. And so that's what we did here. And if you then look at this, you can actually see that this is indeed Vivianite. You can compare it to Vivianite standard. And in fact, what we saw from this is that this is a manganese bearing Vivianite. Next slide, please. Now you know that this is Vivianite. You know, we've proven this in many ways, but then the question still is, how does this matter? To what extent does this matter for the system? So how quantitatively important is this Vivianite in these sediments as a sink for phosphorus? we looked at that in two ways. One is we combined our phosphorus extractions with iron extractions and did all sorts of calculations with typical ratios of iron to phosphorus. And then we could calculate that roughly 40 to 50% of this fraction was Vivianite. We also used our direct measurements from the micro-XRF and estimated the size of these pixels and assumed that the count intensity there told us something about the concentration. And these rough calculations actually gave the same number. About 46% of this phosphorus was Vivianite. And so we conclude here that a very large proportion, in fact, of the total phosphorus here is Vivianite. So we have a major burial sink for Vivianite. And something that has not gone or has gone undetected so far. Next slide, please. Now, so why is this so important at this site? Well, one of the things we think is that at this is an oligotrophic area, and this has become recently more eutrophic. And organic matter has come in, and this sulfate methane transition zone has shifted upwards. And now the sulfide-free sediments are much closer to the sediment-water interface. So this whole zone where you have a lot of iron and there's no sulfide has come much closer to the sediment-water interface. And in this zone, we have a lot of iron reduction going on, possibly also through a process with methane. And we have a lot of phosphate that's being released from the iron oxides that is actually diffusing down and reacting with this iron. And so this is why you have all this Vivianite at this location. Next slide, please. Now, you can then try to develop scenarios to explain this, and we've done that in modeling, but we also did some sensitivity analysis with a reactive transport model. So in that model, you describe all the processes that occur in the sediment. And then we looked at the effect of salinity. And if you change the salinity, what you can see in these graphs is that if the salinity is lower, you get more Vivianite formation and more phosphorus burial. And the higher the salinity, the less phosphorus burial, the less Vivianite formation. That's what you see here on the left-hand side, phosphorus burial rates as a function of salinity, and on the right-hand side, phosphorus burial forms as a function of salinity. And so this is important because it's important in view of climate change, but also when you are looking for sites where this Vivianite might be important, it's especially in this low salinity range in coastal systems. Next slide, please. So to conclude, I've shown you that iron 2 phosphates should be considered in low salinity coastal sediments. They can be identified using a range of geochemical techniques, and they're likely very important, but with variable importance as sinks for phosphorus in coastal seas. And you also saw that that shifts in the sulfate methane transition zone matter. And in our example, this was caused by eutrophication. Freshening also has a very large impact, also generating a wider zone where Vivianite can form and where it can enhance iron 2 phosphate formation. Next slide, please. I'd like to end with some acknowledgements and especially the people that have been doing this work. And I also very much always like this middle picture with the blue color. This is Vivianite that we found at one of our sites. And it's as if someone has painted the sediment, but this is truly the color that we saw. So thank you for your attention.
Thank you very much, Caroline. Very interesting and very nice picture there. So do we have a very quick question for Caroline before we move onwards?
I think we need to move on.
Yeah, okay. We'll try and follow up with questions afterwards. So we move on to Jean-Christophe Ades from Chimera for INCOPA. Please, Jean-Christophe.
Yes. So let me see if I can do that in a smart way somehow. Do you see my screen?
Yes, please just show to slideshow mode.
Yes, here it should be now, right?
Yes, perfect. Thank you very much.
Okay, so my name is Jean-Christophe Ades, and I'm working for Chimera, which is an inorganic coagulant producer. And here today I'm representing INCOPA, who is the Inorganic Coagulant Producers Association, as Caroline already mentioned before. I mean, we are representing 85% of the production capacity in Europe. This is, we are talking about 29 producers and about 80 production sites. And here you can see the European map, and every red or orange dot is one inorganic coagulant production site. And of course, as already mentioned by Ludwig in the beginning, I mean, iron coagulant as well as aluminum, by the way, are essential elements for water treatment, but not only, they are also used widely in paper manufacturing, fertilizer production, and as well as other industries. Now, going to the heart of the presentation, I mean, we have been living in a linear economy since a while, and this is the top part of this slide. And so the phosphorus chain in the wastewater is also following this logic, or was following this logic, may I say, using the past now. So in this world, we have had mined phosphorus, then production of pea fertilizer, then fertilizing the land to produce food, and eventually lost the phosphorus with our wastewater into the sludge. So now, as you all know, the world is switching to a more circular economy, and we want to recover phosphorus from the wastewater and recycle it as nutrient to the fields, and then to close the phosphorus loops. And inorganic coagulants actually are also part of this circular economy since a long time. We have been using a lot of recycled raw materials to produce them. And now by recovering the phosphorus as well as the inorganic coagulants, then we will have a double loop of circular economy. So before recovering phosphorus, we always start with removal, of course. And here you see some elements of phosphorus chemical precipitation. And I will mostly concentrate in this presentation in the two red circle ones. And that is to say that inorganic coagulants are able to achieve ultra low level of phosphorus discharge. And they also chemical treatment has also the lowest carbon footprint of all available phosphorus removal or water treatment technology. So we will see more of those two things in the following slides. So as I said, inorganic coagulants, they can achieve ultra low levels of phosphorus. And here in this slide, I would like to show you an example of Finland. We can see here many plants, wastewater treatment plants of more than 100,000 PE equivalent. And it is possible here, as you can see, to reach rather low level of phosphorus, much lower than the EU standards. And by rather low, I'm talking about 0.2 milligram per liter, and even lower in some cases. We have to admit that bio-P plants are not able to reach these levels. They normally can reach around 1 milligram of phosphorus, which is the EU standard, but in most cases they use some chemistry to support that. So inorganic coagulants are the only way to achieve such low phosphorus levels in the effluents all over Europe, as this data from Finland is clearly demonstrating it. Now, after removing the phosphorus, I mean, we also need to look at how to precipitate, how to be able to recover it from wastewater. And chemical phosphorus precipitation guarantees high recovery rates. By using inorganic coagulants, you can recover phosphorus either from sludge or in the tertiary treatment, and even if not on site, but later from the ashes. And we will see more in detail how to reach this. So here you have some examples of phosphorus recovery processes. So as I said, there are three different ways of recovering phosphorus once removed from the wastewater. So you can either recover it from the sludge, or from the tertiary treatment, or from the sewage sludge ash. For example, when you recover phosphorus from the sludge, You also can recover iron or aluminum coagulants. It can be dosed, the inorganic coagulant can be dosed flexibly, either to the primary, secondary, or tertiary treatment. It needs chemical extraction of phosphorus afterwards, or physical separation, or also biological pathways. Then you have the possibility to recover phosphorus from tertiary treatment. Then you need to install a recovery unit, which is easily installed to the existing wastewater treatment plant. You dose the coagulant in the tertiary treatment. And as well here, in this case, both iron and aluminum coagulants can be recovered as well. And then you have the third possibility to recover phosphorus from sewage sludge ash. Normally this is having a very high recovery yield of phosphorus, up to 90% or more. Most extraction processes, they also recover the inorganic coagulant, but then you also need mono-incineration of the sludge. So my message here is to more or less to say that using coagulants is universal. So if you use an inorganic coagulant in any wastewater treatment plant, you can choose then the phosphorus recovery processes. Now, I said I also would like to present a few words about a recent study that have been done by the Swedish Environmental Research Institute. And this is a life cycle assessment. So we have been measuring the carbon footprint of 3 different wastewater treatment configurations. So here it's a quite busy slide, but you can see what the 3 different configurations were. And so we studied the pre-precipitation, the simultaneous precipitation, and the biological pea removal. Now let's quickly have a look at the boundaries of the system. So in this study, we have used the same incoming wastewater, the same flow, and the same effluent demands. And instead, we have modulated the process to get the data. We have also considered that all plants should have biogas production, and the biogas should be used with the same purpose on all cases. Also, we have considered that only the sludge produced at the wastewater treatment plant was used in the digester. So the study has been done by making models of the different treatment processes and simulate them. So the simulation was done on real-time data over 1 year of operation, including some stormwater events and other disturbances. We have used a very important Swedish wastewater treatment plant. And since all processes have the same raw water and the same effluent requirements, they can be compared with each other. So the parameters that were varying are the chemicals and the energy, the sludge volumes, greenhouse gases, and biogas volumes. We have also studied 2 effluent limits parameters. So we have used the baseline, which is the more or less the EU limit standard, and we have used also a stricter phosphorus limit of 0.3 milligram per liter. And we wanted to see here how that influenced the environmental load of the different process configurations. Here you see more or less the results, and we have analyzed the global warming potential on the three process configuration. And you can see here that chemical pretreatment, which is the 2 first columns. The first one is the baseline phosphorus level, and the dark one is the stricter. So you see that the global warming potential expressed as kilogram of CO2 equivalent per cubic meter of treated wastewater is lower than the 2 other configurations. I will not go through the whole IVL study, but this will be soon published on their website. And so I welcome you to have a look at this later. But I will just go through the conclusions of this study. And those are that chemical pretreatment clearly gives a lower global warming potential than the other configuration. We also know, and IVL has also concluded and confirmed, that pre-precipitation generates most biogas. energy source important factor for several impact categories, and a more stringent effluent limit in terms of phosphorus leads to a higher carbon footprint. And my last slide about the role of inorganic coagulants in the circular economy. So inorganic coagulants are used in wastewater treatment. They are needed to achieve ultra low level of phosphorus discharge in the environment. They guarantee high phosphorus recovery rate, in all cases over 50%, in some cases over 90%. They allow a higher energy recovery from organic waste and hence lead to a lower carbon footprint. And they have also been part of the circular economy for many years. Thank you very much.
Thank you very much, Jean-Christophe. I think we'll have to switch on directly to the next presentation, which is indeed showing where this iron is coming from. I'm quite excited about this one personally. So Denise, I will share your presentation. Oh, sorry. Okay. So we'll now hear from Dennis Roberts, who's from LKAB Minerals, and Derek Enns from Sustainable Water Company. Please, Denise.
Okay, thank you, Sarah. Yeah, next slide, please. So that was just to introduce me. The reason Sarah's excited over this, I think, is because she probably comes from the hometown of Kiruna, which is where the magnetite comes from. LKAB have their own mines in the north of Sweden, and we produce up to 30 million tonne a year of a product called magnetite, which is an iron oxide. It's used as a flocculant in the water treatment industry. It's used as a flocculant to weigh down particulates from the water. It's used to produce ferric sulfate and ferric chloride coagulants. And it's used as a filtration media whilst backwashing through filtration systems. So it's quite a busy old product in the water industry. Next slide, please, Sarah. The Swedish magnetite, the reason that I think it's important to talk about this today is because apart from it being a black hard mineral, it's an extremely pure product. It's iron oxide is Fe3O4, very high in iron content, 65 to 70% depending on the grade, and it has no heavy metals and chemically inert, which I think is extremely important. Resistance to leaching, as we've had tested for our offshore business, and it has a very low water absorption. As I said before, we've used magnetite on a number of occasions within the water industry for different applications to remove phosphate. But we now have a new project that we're working on to produce a pellet for reed bed systems, which is not actually using this product, but another iron oxide. So I'm going to hand over now to our partner, who's a guy called Derek Enns, and he'll introduce himself and his project to you. Next slide, please, Sarah.
Hi, good afternoon. My name's Derek Enns. I'm the director of a company called Sustainable Water Company. Our objective is to produce a media that can be reused if possible, and also to be able to remove phosphates in a tertiary treatment environment. We've had issues in the past with regards to clogging, which has been mentioned on a number of occasions throughout the presentations. So again, using tertiary treatment wetlands or even quaternary treatment wetlands, and that whole process would be something that we would be looking to aim to implement. And I think you can see by the drawing here that there's a septic tank, vertical flow reed bed, willow soakaway, which is then followed by a pool to utilise the media in. It'd be good for rural communities, and with the new legislation that's coming into force, there's projects coming off with working alongside Severn Trent Water, and they're wanting to use to test, at least to test the product to fit whether it meets their criteria. With the use of wetlands, it's much easier to operate and maintain, therefore reducing the costs considerably to the water companies. And there's been a number of companies showing a very great interest in this process. The research is focused on absorption and precipitation mechanisms of the specific reactive materials, mainly ferric hydroxide and other binding materials that we've managed to secure a patent on. The solution was to treat phosphorus. It's a byproduct from the water industry to produce a pellet media to embrace the closed loop technology. Again, we were using not waste, but byproducts from the mine water industry and also from the water industry itself for treated phosphorus from removing drinking water. We've utilised a sensitive binder which minimises the pH spikes, which was the big issue that we've had for a number of years trying to bring this product to market. It's always been pH issues in terms of discharge. Anything above 9 generally indicates that the water companies are not interested in working with you. So we used to have a product that was about 10, 12 on average, but we've managed to reduce that by bringing in this sensitive binder. Next slide, please. So the phosphate reduction from a 24-hour period was around about 50%, I would say. But we can see here that the system we're using is purely passive and gravity fed. The pellets negate the need for additional treatments such as acid treatments. When you have a high pH, you maybe have a quick absorption rate of phosphates, but again the effluent then after that is of a high pH. It's very difficult to allow discharge of these consents. The trials are ongoing with a customer to prove the retention time, which is what we just discussed a minute ago. It's a low-cost solution. It's sustainable. It's helping to encourage a closed-loop technology. It's self-running due to gravity-fed systems. We may well need to add a little bit of aeration at the vertical flow stage, which would encourage nitrogen removal. Again, that could be done with solar panels or some form of pump system. So there we are. It's a long-term natural process solution, which is embracing wetlands and sustainability. It's always been our ambition to remain sustainable within the water market. But again, you know, there's limitations to the size of wetlands and due to the land take that they take. So therefore, trying to embrace smaller footprints is clearly arguable. So that's what I have to say about that. Thank you.
Thank you very much, Denise and Derek. I'm not sure if people in my hometown where the LKB mine is located, if it's ever occurred to them where some of the iron ends up, but for a good cause. Okay, let's move on to the next speaker, which is William Schipper from Schipper Consulting. And I hope we have a few minutes in the end of the session for questions. So William, please. while we wait for William to load his presentation, please use the chat as we are a bit late and we're very little time for questions. So please post your questions directly to the chat, and
you can see that?
Have them. Yes, thank you. That's perfect.
Okay, right. So I would like to speak a little about industrial phosphates, focusing on iron phosphates. So far, we've seen a lot about using iron to make phosphates, and of course, the question is, if you get something, is it also something that people might want? My background is in the industry, and I'd like to tell you a bit about that. Now, the world usage of phosphorus, very briefly, 21 million tons of phosphorus as P as the element per year. As you can see on the top pie chart, by far the largest part of that goes into fertilizers. If you look at the tiny bit that doesn't go into fertilizers, there's part that goes into white phosphorus, top left. To the right is feed, which is an additive to animal feed, and the lower bit is phosphates with a dotted line around. This is the value chain of phosphate rock. On top is this thermal route, which is very minor in terms of volume through P4. The elements to make all sorts of organic derivatives, sulfides, oxides, chlorides. To the bottom is the main route to process phosphate rock through impure phosphoric acid, also called MgA. And in the middle is a section where these two routes overlap. You can oxidize P4 back to acid, or you can purify MgA into a more or less pure form of phosphoric acid, which is almost but not quite identical. And these are the sources for various industrial phosphates. So the main uses are fertilizers, feed, food additives. There's loads of phosphates in your food, even if you don't realize it. These perform things like moisture retention, preservation, and acidity. And a very small segment nowadays, but it used to be big in the past, which is detergents. So the main phosphate types found in industry and floating around on the market, of course, it's not a salt, but phosphoric acid itself. Ammonium salts are of paramount importance in fertilizers, MAP and DAP. Sodium phosphates are the main phosphates found in food and detergents. Potassium is a good second in the food sector, as is calcium phosphates. They're also found in feed phosphates, in toothpaste, organization aids, also medical implants. There's a whole world of application behind it. And there's some magnesium phosphates, which are a feed additive. So conspicuously missing from this list, of course, is iron. Yeah, the question was actually, Chris Thornton said, can you tell something about iron phosphates in industry? I said, well, it's going to be slightly difficult because it's not a big product. That's the short and sweet of it. I've taken a deep dive into major producers' portfolios. You don't see it except for one, which we'll get to, and they will get to today. And you don't find any market studies, such as the really detailed studies by Chr on all phosphate worldwide. You can see it as part of some fertilizers, depending on the soil type. This is a good idea, or in many cases, it's not particularly useful. But I found a niche application, which is an organic molluscicide, snail and slug pellets to combat snails in your garden. This is for home use and for organic applications. That uses ferric phosphate, FePO4. It's not a big market, and actually there's a reason why it's not a big market. If you look at the label, active ingredients, there's 1% of iron phosphate in it, and 99% is something else, inert ingredients, probably sand. So unfortunately, there's not a huge market for iron phosphates. There's one exception, which actually is a really interesting one, which is lithium iron phosphate. You probably familiar with the concept of lithium-ion batteries, such as found in cell phones and electrical vehicles. A cathode is one of four important parts of such a battery. And the cathode is usually made of lithium cobalt oxide, but you can also make it from lithium iron phosphate. Very briefly, it works like this. It's actually a miracle it works. There's a compound LiFePO4 and a compound FePO4. And the reaction is such that you can put lithium ions in and take them out while charging and discharging without changing the structure. These two crystals have exactly the same crystal structure, and you don't destroy them if you take out lithium and put it back in. And it's a small miracle, it works. This is a very good material to make batteries out of. They have a better voltage stability and a higher stability. They don't run away, such as cobalt oxide types. However, as you can see, it's LiFePO4 instead of LiCO2. There's 2 more oxygens, so there's lower energy density by definition. And the conductivity is also a bit lower, so you need to tinker it a bit to make it more conductive. However, this is definitely a material we'll see applied on a larger scale worldwide. It's still not big if you compare it to food markets, for instance. This is an application. For people trying to recycle phosphate from nature, there's a caveat. This is an ultra high purity material. It's actually not so much the phosphate and the iron that determine its value and price. It's just a high-tech material that happens to be an iron phosphate. However, it is an application of iron phosphates. And then there's Vivianite. We've seen it today. And actually, there has been an application as a pigment. It's a really nice blue or greenish color. This is Vermeer's The Procurers. And the tapestry on the bottom, the grayish green is Vivianite. However, I haven't really found any large applications apart from this one. And it's also not a really common pigment in the paint industry. To look around a bit, iron phosphate applications, you always find this application, iron phosphating, which is a really big and very important application if you look at the size of the industry behind it. To protect iron from rusting its phosphatides on the surface. It serves as a corrosion protector, also as a paint adhesion primer. So it is iron phosphate, but it's exclusively made through phosphoric acid acting on the steel surface. So there's no chance to put actually iron phosphate in this application. So if you try to connect the stuff we get from wastewater or from fields to what we need, the recovered iron phosphates are usually impure and are largely incompatible with the existing applications we've seen. And these are quite limited anyway. So this is not really a very optimistic picture, but there are no large promising one-on-one industrial pathways for recovered phosphates based on iron. And actually it ties in with my experience. I've seen a lot of iron phosphates while trying to recycle phosphate, and for instance in the white phosphorus industry, and it always seems to interfere in one way or another. For instance, if you're trying to make white phosphorus, iron phosphate is about the worst material you could use as a starting material. So I wish I could end on a more optimistic note, but there is a gap between what you get and what you need. And in order to really close the loop, we need extra processing steps from what we get, where we acknowledge it's a very efficient way of capturing phosphate, to releasing the phosphate into something that is compatible with the existing industry as we know it today. I'd like to leave it at that. Any questions I'd be happy to answer now or later. Thank you for your attention.
Thank you very much, Willem. You're touching on the object of the topic of how to release and recover all the phosphorus that we trap, and that we'll address in the session tomorrow. But let's hear now from Alexander Vavre from Preon, who might also say something on this topic. Thank you.
Okay. Is it okay? Hello, everybody. I don't know if you see my my screen.
It's perfect. Thank you.
Okay, so I will talk to you about the GetMoreP process. It's a new process that we developed at Preon Technology. The basis is not specific for iron phosphate, but we made some tests. So a little bit in the context. Okay. With the continuous demographic expansion and increased demand for phosphatic nutrients, and coupled with a decrease of the quality of the raw materials and an increasing demand for peer recycling, it's more and more difficult to use these secondary materials in traditional phosphoric acid processes, and there is a need for new processes route. And in this case, we developed a new route that permit to upgrade low quality phosphate sources into DCP, which can be used directly as a feed grade decalcium phosphate, or also it can be used as an intermediate to produce phosphoric acid of better quality. So little process description. there is a two-step process. We have first an attack of the phosphate material by sulfuric acid in diluted condition. Goal is to produce a solution, a mixed solution of phosphoric acid and calcium, monocalcium phosphate. With this solution, we can adjust some process parameters and to reduce the fluorine content, for example, or heavy metals. And this is called pre-neutralization. Then we make a filtration of this slurry, and the filtrate will be then neutralized with calcium source to produce a DCP that will be the final product. For the moment, our results are live and pilot scale tests made on lot of rocks or secondary phosphate source coming mainly from sewage sludge or some residues from phosphate mines. We tested mainly calcium phosphate with some P2O5 recovery around 90%. And in this process, we have production of a byproduct, mainly gypsum, that contains the major part of the impurities. And we have the possibility with adjusting the parameters to produce decalcium phosphate with a quality up to animal feed grades. Concerning iron phosphate, we tested some materials with high content of iron, and we observed lower recovery, some tests with around 60% yield. And we have some problems at this stage is when we make the pre-neutralization, we have precipitation of iron phosphate, so we lose some P2O5, and this increases also the calcium carbonate consumption. At this stage, we need for more tests to confirm the feasibility, and we are open to receive some iron phosphate material and make some lab tests. So thank you for your attention, and see you next time.
Thank you, Alex.
Thank you very much. So that was our last speaker for today. Chris, can you, have you picked up some questions we could direct to the panelists?
I think many of the questions are indeed addressing how you recover the phosphorus when it's mixed with, reacted with iron, and how Vivianite might impact that. So to a large extent that will indeed be addressed in the fourth session tomorrow afternoon. Not immediately easy to see any specific, any questions which are more general that we could deal with maybe at this stage. So I think it's maybe appropriate to thank the speakers. I don't know whether if the panelists have any questions or comments.
Found it really informative. And as I say, the tomorrow's part of the release of phosphorus is really the part that we were sort of struggled with due to the fact that we've not had certain backing from universities and stuff to take it forward. Be sort of doing it as a private company to try and bring it to market is a very difficult thing to achieve. So I'm surprised we got this far, to be honest. So I'm looking forward to tomorrow afternoon's presentations on phosphorus removal, phosphorus reuse.
Yes, there are a number of questions to the speakers about phosphorus removal with different materials, about how long the active lifetime of the material is and what the phosphorus removal capacity is in terms of grams of phosphorus removed per grams of material and so on, and what the costs are. I think those can be addressed by the speakers with different projects looking at different materials for phosphorus removal. The number of questions about life cycle analysis which have come up, and I guess a number of those will be answered with the publication of the Swedish paper that Jean-Christophe summarized. There's a question which a number of people are asking, which is, will the slides be available after the event? The answer to that is basically yes. The webinar is being recorded if technology is doing what it's supposed to be doing, and we will make that recording accessible, so you'll be able to watch it again and again if you really want to. And the speaker slides we will make available after a certain time to check with the speakers that there aren't any corrections or information they wish to add or remove or clarify. And maybe some of them will indeed add some information following the questions, which we will circulate to speakers. And we will also produce a summary report of all the sessions of the webinar, which will be published as a Scope newsletter or as an ESPP newsletter.
Very good, Chris.
Thank you very much. So unless we have any more questions from the panelists, we'll try to keep to the schedule and finish this off at 4 as promised. There were a few questions popped in the chat box in case you would like to ask them directly. No. Okay, so thank you very much, all of you. This is a bit of a new experience to host events online rather than in person. So it's a good way of bringing a lot of people together. You might miss out the coffee breaks, and we've been looking how to solve that. I hope you take advantage of we've circulated the list of all attendees, those that have agreed to share their emails, so you can reach out to each other through that. And indeed make use of the chat box where you can also slightly connect to each other. Okay, thank you very much. And see you tomorrow, where we will have a session on iron phosphates in agriculture, and then in the afternoon. Well, first we'll have the session on iron phosphate in agriculture, then a poster session with the students from the PTRAP project, and then in the afternoon a session on release and recovery of phosphorus from iron phosphates. So I hope to see you there. Thank you.
Thank you. Bye.
Thank you, everyone. Bye.
Bye-bye.
Bye-bye. Thank you.
Yeah. Bye.
Bye-bye.
Thank you.
Thank you, Ludwig. Bye, Carla.
Thank you.